Since we had to kind of rush in period 7 on Friday and we skipped around a little bit, I thought it might help if I just started over with the note sheet. That way, if you need a beginning to end, easy to understand note sheet, you'll have it. If this video contains way more information than you need, then you can just fast forward to the parts that you feel like you need the clarification on. So here we go. In problem 1, it says, what polynomial function has a graph that passes through the points -2, 13, 0, 9, 1, 4, and 2, 5? Okay, when it says passes through, and we don't have very many points, we know that we're looking for a curve with an exact fit to these specific points, not some sort of rough estimate or a curve of best fit. So that's when we're doing the same thing that we actually did back in Unit 4. With quadratics, remember, if we had 3 points, we could find a parabola that exactly passed through each of those 3 points. And we did that by setting up a system of equations and solving the system. And what we were actually using back when we did that was this thing called the n+1 point principle. So the n+1 point principle basically says when we had 3 points, we could find a polynomial of degree 2. So 3 minus 1 is 2. That exactly fit the points. So when we look at this set and we say that we have 4 points, well, 4 minus 1 is 3. So we can find a cubic polynomial that exactly fits these 4 points. So to do that, we're thinking about the format of y equals ax cubed plus bx squared plus cx plus d. But we're also really glad that we have this point 0, 9. We're not always this lucky, but sometimes we are. You know from all the work you guys have done in your Analyzing Polynomials packet that the y-intercept is always the last number in the standard form equation for a polynomial. So we know that d is 9. Sorry, technical difficulties there. There we go. D is 9. All right. So now we can take each of these points, x, y. We can plug in the y, we can plug in the x, and simplify to get an equation for a system. So our first point is going to lead to 13 equals a times -2 cubed plus b times -2 squared plus c times -2 plus 9. When we simplify that equation, we've got -8a plus 4b minus 2c. We would subtract that 9 from each side, so we've got equals 4. Taking the same approach with the point 1, 4, we have 4 equals a times 1 cubed plus b times 1 squared plus c times 1 plus 9. And simplifying that equation, we've got a plus b plus c equals -5. And for our third equation, 5 equals a times 2 cubed plus b times 2 squared plus c times 2 plus 9. And simplifying, notice we're going to have the same coefficients actually as the first equation, just all positives. So 8a plus 4b plus 2c equals -4. So that's the system of equations that we're going to try to solve. Now, back in Unit 1, where the whole point was to learn how to solve systems, we might need to show that we can do this algebraically using linear combination or substitution. But right now, that is not the point of this problem. The point of this problem is that you know how to model it with a system and that you can interpret the solution when you find it. So we're going to take the easy way out on solving the system of 3 equations and 3 variables. We're going to use a matrix. So we do need to show on our paper that that's what we're doing. So we're going to say we're going to use the ref function on the matrix, -8, 4, -2, 4, 1, 1, 1, -5, and 8, 4, 2, -4. We know that when we do the ref, we're going to get basically the identity matrix with a row of constants. So we need to go to our calculator and perform that function. Now, to save myself a little bit of button pushing, I did go ahead and store that matrix ahead of time. So I'm going to go straight to the ref function. So I went into matrix, math, and it's option B down here for ref. And because I have the matrix stored, I can just go to second matrix and I put it in that first position. You would probably go to alpha zoom to get the matrix menu, and you'd probably just type that matrix right on the screen. So I've performed RF, and I can see that my numbers are 1, 0, and -6. So we have to remember what this means. Remember, the matrix is giving me an A value, a B value, and a C value. We already knew the D value. So the polynomial is y equals x cubed, because it's 1x cubed. I don't need to write plus 0x squared, so I'll write minus 6x and plus 9. If you were to graph the 4 points given into your like stat edit, put it in the lists, and then put that equation in y1, when you looked at your graph, you would see that that curve went exactly through those 3 points. So just quick recap, when you're only given a few points, and when you're told to go exactly through those points, not to estimate or find a best fit, you're using a system of equations and you're coming up with the polynomial that way. All right, now we're going to look at the linear regressions, quadratic regressions, cubic regressions. Before we get started, let's just remind ourselves where these regressions are. So I'm going to go back to my calculator. Remember, if I go to stat and calc, I can see that there's a linear regression in step 4, which you probably learned about in Algebra 1. And then in step 5, there's quadratic regressions, which we worked with in Unit 4. But now also look underneath that, there's a cubic regression and there's a quartic regression. So this is like a series of polynomial regressions. Before you start using regressions, it's a good idea to make sure that your diagnostics are turned on. So if you hit your mode button, you'll see this list of settings for your calculator. And you want to look down here, mine are in blue, it says fraction type, answers, and then stat diagnostics. You want your stat diagnostics turned on. If yours are off, take a moment and put them on, because you won't get all the information you need unless those diagnostics are turned on. All right, let's go back and look at the problem. So the problem says, what is the linear model that best fits the data? Okay, linear model, that means linear regression. See the phrase best fit? That's what tells us we're actually doing a regression and not looking for a perfect fit. Also, look how much data there is in that table. For a linear model, I would only need 2 points if I was looking for an exact fit. So that's the other clue that we're really just doing a regression here. All right, so when I see these years and I'm thinking of using years for my x values, those are large numbers to be typing into the calculator, and it gives me really big numbers for my coefficients when I get the model. So I'm going to make the choice, instead of entering those numbers as is, I'm going to define my list 1 to be the x values, where x is the number of years since 2000. So any years prior to 2000 would be expressed with negative numbers, and any years after 2000 will be expressed with positive numbers. It just makes the numbers that I enter into the calculator a little bit easier to do. So again, I cheated a little bit so you didn't have to sit here and watch me push buttons. I went into stat and edit, and you'll see that all my data is there in list 1 and list 2. So obviously you would have to do that, type those numbers in there. If I'm getting a linear regression, I'm going to go back, hit stat, choose calc, and number 4 for linear regression. I always want to verify that my X list is coming from list 1 and my Y list is coming from list 2, because that's where we put our data. We don't care about frequency list for this type of work, but we do need to store our regression equation. If you've looked ahead in the note sheet at all, you can see you're going to be asked to calculate a linear regression, a quadratic regression, and a cubic regression. We want to keep all those regressions at the same time. So it's very important that I store this one in Y1. Notice I hit alpha and then trace to get this submenu, and I'm telling it to store my equation in Y1. When I go to do the quadratic regression in a minute, I'm going to store it in Y2. And then I'll store the cubic in Y3. And that way I keep all of the information and they don't overtype each other. I go down to calculate. The computer does some work, and I now have the slope for my line in A, the y-intercept for my line in B, and then I have this r squared and r values. Well, r is technically the correlation coefficient. Remember back to quadratics and probably linear back in Algebra 1, that the correlation coefficient tells you how strong the relationship is between the points you have in your data and the curve or line that you're using to model that data. A perfect fit, so every point being exactly on the model you've chosen, would be a correlation of 1. It's like 100% fit. The worst you can have here, actually in R, would be a -1, but really, it would be a 0. So everything's between 0 and 1. Sometimes with lines, you can see negative numbers for the r, and it just relates to whether the slope is positive or negative. Because other curves don't have slopes the way a line does, we tend to compare the r squared value instead because it's consistent for all the different models. So when I go to write this information on my paper, I'm going to include the r squared value. So I go back to my work that I was doing. First, I'm going to write the linear model. We've got y equals 1.2854. It looks like that 54 is repeating, x, plus 247.0109091. All right. And then I'm also going to record that r squared because it's kind of like a score saying how good this model is. Now, if you remember just a minute ago, I said that the model, the r squared is the correlation coefficient, and that 1 is the best it can be. Notice this is really far from 1. This model is not a real close fit. So let's look at a couple things. First of all, I look at that y-intercept from my model. Notice 0, right, was the year 2000. 251 should be the y-intercept if I'm using the real data. 247 is like in the ballpark, but it's not exact. So right away we can see this is certainly not an exact fit. In fact, we could even take a minute now that I'm not in class and rushing, and we could look at this. So I'm going to set my window at like -5. I'm trying to remember, I think we only had like 18 years shown, so I'll go to 20 and I'll let it count by 5s. And then for my y-mins, my y-min can be, I'll set that as -5 just so that the axis shows up. And then I think our highest values was in the upper 200. So I'll just go to 300 and I'll let it count by 25s. And I'm going to look at my graph. So I can see that I've got this data that almost looks like this little wiggly curve happening, and then I've got this straight line passing through it. So, I mean, it's not a terrible fit. Some of the points are above the line, some of the points are below the line. It's kind of distributed, but it's not a great fit. You can see why the correlation is only at 0.4. All right, let's see what else we're asked to do in this problem. It says, use the model to estimate egg consumption in these years. Okay, when we're using the model, that means we're substituting values for x and finding out what y is. Now, you can do this out by hand, but you're dealing with tons of decimal numbers, so it's not that fun. It's very tedious. So there's a handy way you can do this in the calculator. You can essentially use a modified form of function notation. If you remember back, if I say f of 2, that means evaluate the function at x equal to 2. So this is like that type of notation. It's how you communicate it to the calculator. So 1970 would be 30 years before the year 2000. So I'm going to do essentially f of -30. 1995 would be 5 years before. 2009 would be 9 years after. And 2045 would be 45 years after. This is how the notation looks in my calculator for me to say to the calculator, hey, I want you to evaluate each of these numbers. So I'm going to come in here. I'm using second quit to get out of there. I'm going to use alpha trace to get my y1 right on this main screen. I'm going to open parentheses and type -30 and then close my parentheses. What I'm doing is asking the calculator to substitute -30 in for x in my function and solve for y. I'm going to do that for each of my values. So we wanted to know 5 years before, We wanted to know 9 years after, and we wanted to know 45 years after. All right, and I'm going to cheat a little bit. Instead of typing that, I'm just going to snip this and put it right in to my note sheet. It's probably easier to read than my writing anyway. Okay, next we're going to be asked in part 3 to take a look at creating a quadratic model and then to use that model to estimate the egg consumption in each of the same years. So I'm going to repeat the process. Conveniently, I already have my data in the calculator. So I don't have to put the data in again. I just have to go to Stat Calc and choose a quadratic regression. I'm still working off of list 1 and list 2, but remember I mentioned before, I want to store it in Y2 this time so that I don't overwrite my equation. I keep both equations. And now I have this quadratic model that I can record. Okay, so I put the information over here so it'd be easier to write the model. So I'm going to write that my model is y equals 0.207075758x squared minus 2.4406818, looks like that 18 might be repeating, x, and then plus 256.9472, and that looks like it's repeating as well. And I'll go ahead and record that correlation coefficient of 0.744. So right away we see this is a significantly better correlation coefficient than what we had with the linear regression. So we would expect that if we take a look at this curve, it's going to look a lot more like it fits the data. So there's the old linear regression, and now we see a quadratic. So I would agree that that looks like it's a little closer. Notice how that like dip of the points in the middle is pretty close to that curve on the bottom. Some of the points are actually right on the curve, so it seems like a better fit, but it still doesn't really seem like the same shape, so it's still not an ideal fit for the data. Now let's also compare this one other way. So if I look at this model, it says my y-intercept should be around 257. If I go and look at the data, remember the y-intercept is 251. So although this model is technically a closer fit, we're kind of even further away from our actual y-intercept. So I'm still not feeling like the fit is fantastic. I do need to evaluate each of those numbers. So I'm going to go do the exact same thing in my calculator as before, except this time I'm going to use y2 and ask it to calculate each of those values in y2. Again, rather than rewriting all of those values, I just took this calculator screen and you can see the calculator substituted -30, -5, 9, and 45 for x, and then solved to find out the values. So let's take a quick moment. Let's compare some of these things. So according to the linear model, in the year 2045, people would expect to be consuming about 305 eggs annually, whether that's eating up egg by itself or eating bits of egg in the other foods that you eat. Whereas according to the quadratic model, in the year 2045, we would be expecting people to consume like 566 eggs. That's a really dramatic increase compared to what we've seen so far. But if we compare something like 2009, according to the linear model, it's about 259 eggs, and compared to in the quadratic model, it's about 252 eggs. So those aren't so different from each other. And if we look back at the actual data, we would maybe expect from the actual data we'd be somewhere in the upper 240s. So we're a little bit off from that, but again in the ballpark. So it's sort of interesting that the models with small numbers like 2009, only 9 numbers off of 2000, the data seems kind of reasonable for the answers, whereas as we start to look further out, it looks a little less reasonable. All right, let's do the cubic model and then we can kind of finish our big picture view of this. So for the cubic model, we're going to go back to our calculator. We're going to do second stat calc, and we're going to choose cubic regression. If we wanted to, we could do this a fourth time and do quartic regression, but we're going to call it quits after cubic in this particular case. We're putting it in Y3 this time, again, so that we keep all three models together. And just as we did before, we're going to record that information. We're going to look at the correlation coefficient and write the model. So I can see that my cubic model should be y equals 0.017814297 x cubed minus 0.256891025 squared plus 0.7275738 151x. I'm running out of space, so I'm going to slide this over. Models get really long with these long decimal coefficients. Plus 253.4834965. And we have a correlation coefficient of 0.791. So we didn't see the huge jump in a model that's way more accurate this time that we saw between linear and quadratic. This time we only went from 0.74 to about 0.8. So it is still an improved model. It's more accurate. If we go look at the graph, there was the linear, there was the quadratic, and now we see the cubic coming in. Notice that gets more of that wiggly shape going on in there. In fact, if I go to y equals and I turn off those first two so that we only see the cubic, it'll actually be a little bit more clear. Look how that does start to have that kind of S-curve going in there. Suddenly with this model, when I'm looking at this data, I'm like, oh, that looks kind of like what's actually happening with the shape. Although I have to say, I almost feel like it should curve back down again. It makes me curious about a quartic model. Let's just take a moment and let's look at it and see what happens if we throw a quartic model in there. It's not required as part of your work, but I'm kind of curious as to how close a fit it would be. And while we're here, it's not that hard to do. I'm going to put it in Y4. All right, so we're calculating. I'm not going to take the time to write it out. I'm just going to peek at the graph. Now we really see it taking that shape. Look at that model. It hits almost all of the points. And if we go back and look, oh, I think it's up here. Let's grab that model again so we can see the correlation coefficient. Look how strong that correlation coefficient. We're at a 0.92. So it's a really strong correlation coefficient. This quartic regression really fits that data quite tightly. All right, but let's go back and talk about the models at hand. We've got this cubic model. Notice that y-intercept of 253. That's much closer to the 251 from the real data. Just like before, I do need to ask my calculator to do the Y3s, evaluate using the cubic model to find out what's going on in each of these years. So let's take a peek at that. Something interesting has happened with this data. Notice my Y9 is 251, so 2009 is now predicted to be 251. That's actually a little less similar than some of the other ones. But look what's happened in like 1970. We're consuming a negative number of eggs. Like that's not even possible. And in the year 2045, we're at over 1,300 eggs. So there's something interesting happening with this data. So I had snipped here. If we zoom out, the stuff happening in 2045 would be out here. And the stuff happening in 1970 would be back here in this region. And all of a sudden you can see how the cubic model is coming up with a negative number. Notice it jumps right off the screen down here. So we get to this interesting concept of interpolation versus extrapolation. Interpolation is when you use a model to predict within a data set. So that was like looking at 2009. That was a value that you weren't given that fell between two values that you were given. Each of the other values you were asked to look at fell outside of the data set. So that's when extrapolation comes into play. So with extrapolation, you use a model to predict outside of the given data. So what we see is when we're trying to determine what's the best model to make a reasonable estimate about what's going to happen, we have a different problem-solving process for interpolation versus extrapolation. With interpolation, we're going to rely on the correlation coefficient. If you notice, as we went from linear to quadratic to cubic, and even that extra quartic that we did, the higher the power on our model, the closer the curve came to really touching the data. So when we're talking about fitting within the data set that we're given, you'll get a better estimate by improving your correlation coefficient, which typically means doing a regression with a higher degree. But for extrapolation, we don't always want to rely on the coefficient. Sometimes we want to take like what we would call a bird's eye view. Let's look at this set of data and look at those models in this little sketch that I have off to the side. If I'm thinking realistically and I want to look outside the data, so say I pick a value here, here, here. I really need to think about that data. When I zoom out like this and I look at all the actual data in here, that data is really not changing all that much over time. When we were up close to it, it seemed like there was wide variation from one year to the next. But when we zoom way out, we can see it's actually all happening within this little band. So if I'm looking way outside the data, like at the year 2045 or way back to the year 1970, that cubic model, or certainly if we had looked at the quartic model, definitely not that model, those models are really not that accurate so far outside. Even though the linear model had a terrible correlation coefficient when looking at the actual data, the linear model is personally the one that I would use for extrapolation. Because in the big picture view, it's less susceptible to the whims and the small fluctuations. I would be much more likely to believe a value out here for the year 2045 than a value way up here. It just doesn't seem realistic. All right, I hope that helped. It's a much more cohesive view of the notes than what we had in class for period 7. And if you were out and maybe you were a period 4 student, I hope this gave you a good idea of what we talked about today. Good luck with your homework.